with the concepts we're dealing with, there's a mathematical operation, mathematical notation that we need to introduce, which deals with summation. Sometimes we call it sigma notation. And the sigma, this, that's not what I want. This right here is the Greek letter sigma, capital sigma. You'll actually learn a little bit of Greek as we go through mathematics and, of course, science. A lot of Greek letters are used as scientific symbols as well. But sigma notation is, it's a way to shorten up how we write sums. And just to give you an idea, some of you may have already seen this before, but to give you an idea what we're going to be using, we're going to go ahead and write out the terms represented by these summations. And the first one says the summation I equals 1 to 5 of the expression I squared. So what that means is we start with this value, of course 1 in this case, and we're going to plug in 1 for the I in this expression. So the first term would be 1 squared. Second term, we continue on up, 1, 2, 3, 4, and then 5 would be our last term here. So 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And that's what this summation represents. Now, of course, you guys could all multiply this out and add it. At this point, I'm not real worried about those skills that you have. I'm pretty sure at least you'd be able to use your calculator and find these, or at least hopefully. But notation is the key we're going to focus on here. Now, some of the terminology we use, I in this case, in the first example, I is called the index. Now, most of the time, summation, we use I, sometimes we'll use J, sometimes K. Those are the more common ones. Once in a while, we'll even use N, but usually I or J or K are the ways we see this. And in our second example, we've got the summation as K goes from 5 to 7 of 1 over K. So in this case, the index does not start at 1. Okay. Well, to represent what this summation is, 1 over K starting with 5, then 6, and then 7 being our upper limit there. So that summation would be written these 3 fractions. Okay. Questions on the summation notation? Now the summation or sigma notation, it's important for us to be able to look both directions. Given the sigma notation, write it out term by term. In this case, we're going the opposite way. Here's an expression written term by term. What should it be in sigma notation? So this is going to equal, and my Greek writing is a little off. You guys, I've seen you guys write better than that, but sigma, well, we would say our expression we're applying the sigma to would be what?
7 times I over 6 plus 5.
Okay, 7 times I over 6 plus 5.
It starts at 1 and ends at 6.
Okay, we see the 7 shows up in each part. The plus 5 shows up in each part. Those two pieces do not change, so we don't need I at that part. Also, the denominator of our fraction remains the same throughout. The only thing that's changing is the numerator. And the dot, 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 most of the time we don't want to write out all of the terms. That's why we've created this shortcut notation. Some people think mathematicians are lazy. I kind of prefer the term efficient. We create notation to make things a lot easier to write. But the only thing that's changing is the numerator of this fraction, and it's going from, well, 1 up to 6. So the index I equals starting at 1, ending at 6. And this would be the summation notation or sigma notation representing that sum. Okay? Now, some of these are fairly straightforward, fairly obvious, but there's some that get pretty tricky. So, questions on that one? Now, what we're leading up to here will also lead up into our definition of the definite integral. And there's a lot of information that we're going to look at on this problem, a lot of steps, but again, it's kind of the basis for what we're leading into with the definition of the definite integral. What we're going to be doing is, well, we're going to approximate the area above the x-axis from 0 to 2 and under the curve x cubed plus 1. Now, we're going to do that by using easy geometric figures, nothing easier than a rectangle. Area of a rectangle is simply length times width. And we're going to do this in several different pieces. First of all, part A says use the left endpoints and part B the right endpoints. I'll explain what that means as we go through the problem. But another thing, how many rectangles are we going to use? For each part, we're going to use 4 rectangles, and then we're going to turn around and do it again using 8 rectangles. And then we'll kind of see what happens from the results we get, and we'll be able to kind of at least estimate what the exact area is going to be. At this point, we're not going to be able to find the exact area, but we're going to be able to get pretty close by the estimation. Now, to get a little bit of an idea here what's going on, let's go ahead and look at the graph of x cubed plus 1. And from 0, if x is 0, y is 1, x is 1, y is 2, and x is 2, y is going to be 9. I never leave myself enough room here. But the graph is going to look like this. Oops. And then we're going to find, or not find, but we're going to estimate this area, this nice little, well, 3 sides of it's pretty nice to work with, but that 4th side, that top, is curvy, and we're not going to be able just to use rectangles to get the exact value, but we will at least approximate it. And okay, first of all, using left endpoints, what does that mean? Well, we need 4 rectangles going from 0 to 2, 4 rectangles of equal width. The width of each rectangle is going to be what? Okay, 1/2. Now, notation-wise, we like to use delta x here because we're changing from x equals 0 to x equals, well, 1/2 will be representing the width of the first rectangle, and then 1/2 to 1, 1 to 1.5, and then 1.5 to 2. Those will give us the 4 widths that we're representing. And there's a quick little way, of course this one's easy enough, you can figure out without this little formula, but quick little way of calculating the equal widths. This only works if each width is to be equal, but we say it's b minus a over n. Now, the a and the b represent the x values, the interval we're looking at. So from 0 to 2, the numerator here is essentially the length of the interval, length of the overall interval we're looking at. And then we're splitting this into 4 parts, n equal 4. So, yeah, as you do the calculation there, we do see delta x 2/4 or 1/2. Okay. Now, that's really the key to being able to set this up as smaller parts, smaller to represent it as rectangles. Now, I'm going to jump to the next page and we'll take a better look at what the what this represents, how that shows up in the area, but we'll draw the graph a little bit bigger and use a better representation of what those rectangles mean. So x cubed plus 1, and go from 0 to 2. And getting extreme accurate with the graph isn't real important, but at least to give us an idea how this is represented with the rectangles, that's important. Now the width, we said, the first rectangle would go from 0 to 1/2. What is the length going to be? Or you might think of it as height, as we kind of... Okay, we're to use left endpoints, and we need to identify that to say how far up are we going to go. We're going to run into this function, but to see how high we go with it, we need to say what x value are we going to use. And in this case, left endpoint, we'll be using x equals 0 for the height of our first rectangle. So graphically, we could say there is the rectangle, our number 1 rectangle. Okay. So f of 0 equals 1, that's going to be the length of our first rectangle. And the width, well, again, that's our delta x. Okay. Now, we'll kind of start pulling all of this together. The area is going to be approximately, well, the area of this first rectangle, which would be length times width, plus, well, moving to the second rectangle, we're going to use what? Width again will go from 1/2 to 1. How do we calculate the height or the length? Okay, we use the left endpoint, which this time is 1/2. So our length is going to be f of 1/2. Plug 1/2 into the function and get our value. And then again times the width, which will be 1/2. Then our third rectangle will go from 1 to 1.5, or 3/2. And the length of it, again using the left endpoint, we'll hit the curve here. So the length will be represented by f of 1. And then finally our fourth rectangle, left endpoint. Okay. And with this, 1.5, 1.5, 3/2, whatever you want to use there. I'm not real picky on the form that you use. We'll get probably a good decimal value for this anyway. So, but this would be the way we estimate the area using 4 rectangles and using left endpoints. Okay, we used x equals 0, x equals 1, 1/2, I guess, then 1, then 1.5. Now notice we did not use x equals 2 because that last rectangle was calculated, the height was calculated from the left endpoint, the 1.5. Okay. Now calculating this, well, that came from f of 0, so notice each one of these has the 1/2 multiplied by it. Because we have equal widths, we could really shorten this notation up to, and I'm going to go back to the function notation here, f of 0 plus f of 1/2 plus f of 1 plus f of, well, let's go 1.5 this time. And then factoring out the 1/2 from each term, all of that's going to be times 1/2. Now you can kind of start to see where this summation notation might come in. And with today's example, we're not going to switch over to the summation notation, but as we further examine the definition of the definite integral, we will be throwing this into that sigma notation. So we've got a little bit of work to do before we do that. But this would be our approximation using 4 rectangles with the left endpoints. And somebody want to calculate that? Probably the hardest thing, or where you're going to make the most mistakes, is getting things correctly put into your calculator. So we got, what, 6.68? Okay. And that includes the adding all the function values together, and then one easy thing to do is to forget multiplying by the 1/2. So make sure you do that as well. So one estimate of the area is 6.68. Now, is that, well, it's a good estimate, but is that over or under the exact area? Okay, it's going to be under. As we look at our picture up here, we can see we're not counting these little areas right here. Okay, the rectangles kind of fall short from covering all of the area. Well, let's go ahead and shift over to the part B using the right endpoints this time. And I'll go ahead and go to the next page. Now, whether we're using the right endpoints or the left endpoints, because we're still looking at 4 rectangles here, delta x is still going to be 1/2. So we're still using what we will eventually call the partition. We're still using the same partition of 0, 1/2, 1, 1.5, and 2. But this time we're going to shift to the right endpoints. So instead of drawing our rectangle up to the point 0, 1, we're going to use 1/2, and the length of that rectangle will be f of 1/2. Now that's our first rectangle this time instead of using f of 0. Then our second rectangle, we'll use f of 1 as our height. Third rectangle will be f of 1.5 as our height. And then finally our last rectangle, the fourth rectangle, will be f of 2 for our height. And that one, of course, is an easy one to calculate. It'd be a value of 9 on that. But we get still using 4 rectangles, still having half as our width of each rectangle. We're just shifting the heights. The heights end up being taller for each of the rectangles. But as we write this out, the first rectangle, f of 1/2 times 1/2 would be length times width. F of 1 times 1/2 would be our second rectangle. F of 1.5 times 1/2 would be our third rectangle. And then finally our fourth one, f of 2 times 1/2. Or, as we showed earlier, we could again factor the 1/2 out, and we'd be looking at these values. Now, we've already used these 3 values in calculating the left endpoints. Well, they're also right endpoints of the 3 of the rectangles, but we'll be using f of 2 instead of f of 0 that we used in the left endpoint. So there's going to be a lot of repeat numbers. Some of you will be able to kind of figure out the shortcut in calculating this part once we've done the part A. But calculating this one, we get what? So we end up with 10.68, which, again, a good approximation. Is this going to be more or less than the exact area? Okay, this one's going to be more because the rectangles go above the curve. We're actually counting more in this approximation than we should be. So what we find from part A and B for this first step using 4 rectangles, the exact area is going to be between 6.68, which we found using the left endpoints, and 10.68, which we found using the right endpoints. Okay. We know that the 6.68 is less than the exact area because of how we drew the rectangles. This one is more by that much, but the exact area is somewhere in between. Now, how do you think we can get a better estimate? And this is pretty good, somewhere between, well, around 7 and 11, rounding up on both of those. How do you think we could get an even better estimate? Okay, use more rectangles. And the first part of the problems you'll do on your worksheet will have n equal 4 to begin with, and then I'll have you turn around and do n equal 8, which instead of having just 4 of these, you'll have 8 function values to calculate. Your width will be a little smaller, but same calculations. We won't go through part 2 on the n equal 8 today in class, but that'll be something on the worksheets you'll have to do. But those numbers will actually, well, we can graphically show you what happens when n equals 8. It's going to cut the width in half. The width will be 1/4. So the first rectangle will be that. Second rectangle will be this. We'll kind of zoom in on that first rectangle. There's with n equal 4. But if we go n equal 8, okay, we would be getting that much closer. This amount would be out of the n equal 8. Okay, we're looking at the n equal 4. So we've gotten that much closer. We're still going to be above the exact value, but it's probably going to be maybe more like 8 or 9 instead of the 10.68. And then your left endpoints probably be around 7 to 8 instead of the 6.68. So the more rectangles you use, of course, the more work it is, but the closer we get to the exact answer. Okay? And I think we'll stop there with the explanations. Any questions before we move to our worksheet?